Good afternoon. My name is Samarth Rishi, and I am a student here at VIT Vellore, and my registration number is 24BI0234. And today, I'm joined by.
Hello, my name is Mahit Singh Saini and my registration number is 24BAI0219.
Hello, my name is Ishaan Awasthi and my registration number is 24BAI0207.
Today, we will be presenting our project, a CPU bottleneck analyzer which is designed to simulate instruction execution in a pipeline processor and identify performance bottlenecks.
The main objective of this system is to answer a key question. Why is a given set of instructions taking longer to execute than expected? Instead of theoretical analysis, our system performs a cycle level simulation to give concrete insights.
Before we proceed, let's have a look at how this is related to computer architecture and organization.
This project directly applies to CAO concepts such as instruction pipelining, hazards, instruction latency, and resource conflicts. We simulate how instructions move through pipeline stages and analyze how dependencies introduce stalls.
So instead of just studying pipeline diagrams, we actually model the behavior of a pipeline CPU and measure the performance impact.
Now, the input to our system is an instruction trace file which contains sequences of instructions like add, multiply, load, and store. Each instruction is then passed into three components: the opcode, destination register, and source registers. This is so that dependencies can be tracked independently and accurately.
Once the instructions are passed, they are passed into the pipeline simulator, which is the core of our system. The simulator models how instructions would execute in a pipeline CPU, tracking when each instruction is issued and when it completes.
To do this, we use a latency model. Each instruction type is assigned a fixed execution time. For example, an arithmetic instruction like add would take one cycle, while more complex operations like multiply take three cycles, and memory operations can go up to five cycles.
Before proceeding ahead, let's have a look at how it works step by step.
Sure. First, the system reads the instruction list and passes each instruction. Then, it checks register dependencies and memory availability.
Based on this, it decides when an instruction can be issued. If dependencies exist, the instruction is stalled until the next required resources become available.
After issuing the instruction, the simulator calculates completion time using the latency model and stores all timing information in a timeline.
Now, in an ideal scenario, instructions would flow through the pipeline without any delays, and that would mean one instruction is issued every cycle. However, in real life and in practice, instructions often have to wait due to dependencies or other resource conflicts. These are called stalls.
The first major source of stalls we model is data dependency, specifically raw hazards, read after write.
To explain that, if one instruction produces a value in a register and the next instruction needs the same register as an input, the second instruction cannot proceed until the first one completes. This waiting time directly contributes to the RAW stall cycles.
The second major source of stalls is memory contention. In our model, memory is treated as a shared resource. So when multiple load or store instructions occur close together, they cannot execute simultaneously and must wait their turn.
This leads to what we measure as memory stall cycles. This can significantly impact the performance, especially in the case of memory heavy workloads.
In addition to these, we also track WAR, write after read, and WAW, write after write hazards. These do not cause stalls in our current model but are counted to give a complete picture of instruction interactions.
For every instruction, the simulator calculates three key values: issue time, completion time, and stall cycles. These are stored in a timeline, which represents the full execution behavior of the program.
Now, once the simulation is complete, we compute the total execution cycles. This will reflect the actual performance of the CPU under these conditions.
To evaluate efficiency, we also calculate something called the ideal cycle count. This assumes a perfect pipeline with no stalls, meaning one instruction is issued every cycle and latencies overlap optimally.
Using this, we compute efficiency as efficiency is equal to ideal cycles upon actual cycles into 100. This gives us a clear measure of how close the system is to optimal performance.
Now, the next step is the bottleneck detection. We compare the total cycles caused by different factors, which is the primary data, dependencies, and the memory delays.
If memory stalls dominate, the system is classified as memory bound. If raw stalls dominate, it is data dependency bound. Otherwise, it is considered balanced or compute bound.
Now, looking into the front end, let's have a look at what the user actually sees when running the program.
We build the front end using Streamlit. It provides an interactive interface where users can input instructions or upload an instruction trace file.
After running the simulation, the interface displays metrics such as ideal cycles, actual cycles, efficiency, and detected bottleneck.
The simulation also includes a graph showing stall cycles per instruction, allowing us to visually identify where exactly the delays are occurring.
Additionally, we provide a detailed execution log where each instruction is shown along with its issue time, completion time, and stall duration.
This enables step by step tracing of the pipeline behavior.
Now, the final inference from this project is as follows.
The main inference is that instruction dependencies and memory delays significantly impact pipeline performance.
Programs with many dependent instructions introduce raw hazards, which increase stall cycles.
Similarly, frequent memory operations create memory stalls that reduce pipeline efficiency.
So, in a sense, this tool helps us identify performance bottlenecks and understand CPU behavior.
To summarize, this system models core computer architecture concepts such as pipelining, instruction latency, and hazard detection, and translates them into measurable performance metrics.
It serves as a practical tool for understanding how low level instruction behavior impacts the overall CPU performance, thus bridging the gap between theory and real life execution.
Thank you.